Okay, so let's take a look at another example here. This time we want to find dy dx. So just the formula for the derivative in terms of t. And then we want to determine from that where the curve will have horizontal or vertical tangent lines. And so our equations here are x equals 2 sine of t and y equals 3 cosine of t, as t ranges between 0 and 2 pi. Noticing it includes 0, but is strictly less than 2 pi. Okay, so first of all, to compute dy dx, we just do the derivative of the y function. So derivative of 3 cosine of t, so that would be minus 3 sine of t, and then divided by the derivative of x, which would be the derivative of 2 sine t, which would be 2 cosine t. Okay, so this is, in other words, negative 3/2 the tangent of t. Will actually give us the slope of the tangent line. I always like this example because here the slope of the tangent line is actually given by a tangent. So I think that's just kind of a nice little pun. If you know it, but math teachers really like puns, and we have lots of punny jokes, or at least I do. Again, punny, not funny. So now we ask the question, when would this thing have a horizontal tangent line? Well, it would have a horizontal tangent line when tangent is 0, or alternatively, when the numerator of that fraction is 0. It will have vertical tangent lines anytime the denominator is 0, or alternatively, when tangent's undefined, or when cosine is 0. So we basically can solve this problem by looking for the horizontal ones by setting sine of t equal to 0. And we recall that sine of t is 0 at 0 and at pi, also at 2 pi, but our graph stops short of 2 pi, so 0 and at pi, and cosine of t, of course, is 0 at pi over 2 and at 3 pi over 2. So at 0, when t is 0, in other words, sine of 0 would be 0, so x would be 0, and y would be 3. So at the point, so we have horizontal tangents occurring at the point 0, 3, and also at pi. So again, we plug in pi, sine is 0, cosine of pi is -1. So at 0, 3, and at 0, -3, we're going to have a horizontal tangents, and we're going to have vertical tangents, tangent lines, at these points, which would occur if we plug pi over 2 in. Sine of pi over 2 is 1, so 2 times 1 would be 2. 3 times 0 would be 0, so at the point 2, 0, and at the point -2, 0. Okay, so those are where our horizontal and vertical tangents are going to happen. So that finishes the question, but I do want to show you the graph so we can see exactly what are we dealing with here. So there's my function, 2 sine t, 3 cosine t. Again, I've set it up. You write them in as an ordered pair with t as the variable to do parametric equations on Desmos. And then the constraints 0 to a. Here I've set a to go from 0 to 2 pi, and I've also set it with a step of pi over 12. That's a 15-degree angle. So let's just watch the graph as we increase a come about. Well, one graph, there we go. A, so you can see here at pi over 2, I've hit my first vertical tangent line. All right, there at 2, 0. The graph continues to swing around down to -3, where I hit a horizontal tangent line. -2 on the y, where I hit my second vertical tangent line, and back up to 0 here, where my first horizontal tangent line was at. So we actually have an ellipse here. This is actually the equation of an ellipse. Okay. So we can see the two places there at 0, 3 and 0, -3, where we have our horizontal tangent lines, and at 2, 0 and -2, 0, where we have our two vertical tangent lines. Okay, so we're going to be coming back to the slopes of parametric equations later on. There's a primary reason that we talk about slopes of parametric equations. It's not just because we're interested in them on parametric curves, but this is actually going to be something that's important to us a little bit later on as we continue into this chapter.